from that. All right, heat capacity of A equal to the heat capacity of B equal to the heat capacity of C. Probably could have guessed that. So that's kind of how you need to think about when it has this little extra subscript, you know, the A. What does that mean? It means that's how much heat is generated or released per mole of A consumed since it's a reagent. So this is the form of the Arrhenius where you're given a rate constant at a temperature, and this gives you the rate constant at any temperature. So here, you were given the rate constant at 300 of 3.3. You're given E1, which I'll put up here in a second, and so you can use this equation to give you the rate constant at any other temperature. The activation energy for this first reaction is 9.9 kcal per mole. Been using joules the whole time, and then he switches to kcal. I can't read this, but I'm pretty sure it's a 4.6. What the hell is that? One sec. So we get all this up here. Yes?
Could you be a bit more explicit when you rearrange the energy balance? Because I'm not seeing how the negative delta H reaction is following out. And also, where are we getting the second tau?
Where are we getting the second tau?
We have tau K1, tau K2. In the second tau, the very bottom equation.
No, I know. I know what second tau you're talking about. It should be this one missing one. Yeah, I feel like the rate of 2B is missing one. Let me look in the notes.
I mean, it could be I'm just very bad at algebra. It's not called.
I think it comes from here. See how you have that brings up another tau here and here, because the volume is equal to tau times the initial concentration. So one comes from the rates,
Right.
but then the initial concentration's gone because we had V times initial concentration, so it's related back to tau. not this, sorry. I had that backwards. Tau over C A naught. Volume divided by the initial flow rate is equal to the volume divided by the initial volumetric flow rate times C A naught, which is equal to tau over C A naught. So yeah, the C A naught times V is tau. Does that help? That's a good question though. He does kind of skip a lot there.
Then why is it not delta H reaction, like negative delta H reaction in that formula? Are you just
In this
combining a
one?
bunch of signs? Yeah.
Because there's two minus signs there to start with.
So you
So
just
the
combine
minus signs have ended up in our rate equations.
Okay.
Which maybe that one should, no, that one shouldn't.
Move them around. You just threw the negative signs elsewhere.
Yeah, I mean, you could have left them in terms of, you could have written this in terms of negative R1A and negative R2B and then the negative delta H's, that's fine. But instead, they just, you know,
Okay.
the two minus signs canceled and then the minus signs end up in how you're defining, we're not defining it as rates of consumption anymore, we're defining this as rate of production.
And you make that switch Y.
Just because there was two minus signs.
Okay.
And you don't have to do it that way.
Okay.
It's just, that's what the notes did, so I
Okay,
followed
that's
it.
just- Is that a Vogler thing or is that a Weaver?
Probably a Weaver thing. I feel like most of the time in the book he leaves them as minus R and minus delta H. Weaver just probably felt silly writing two negative symbols multiplied by one another. But is that clear where that comes from? There's a concentration term in the rates that has also disappeared. And that's because the concentration that's in the rates times the volume is equal to tau. So that initial concentration of A also disappeared. And that's why there's an extra tau that has shown up. And then why are they negative in this form? It's because everything's on the right-hand side here, and I moved two of the terms over. So the negatives come back for the delta H's, but stay gone for the rates. So, yeah, sorry, I know it's a little, that was a lot in one step. Okay, so let's plot G and R and see how many intersections we get and therefore how many steady state solutions there are to this problem. I'm going to leave that on the board. And again, it's hard. I don't know if everybody saw this. The whole left-hand side here is the generation term. So in your notes, you can do it a little bit neater than I did. All right, so what does the heat removal term look like versus temperature? Straight line. And what about that mess on the left? Curvy. How many curves? 4 technically, but I know what you're after. Well, I don't know. It depends on how you define a curve, I guess. It's a sigmoidal curve, but there's 2 regions. So it does like that. So I don't know how you define a curve. So how many steady state solutions do we have? Too many? That's a good answer.
How do you know by looking at it that it has that occurred?
I don't. That's why I gave you all those numbers, and then I just did erase.
It in your head, basically.
Yeah, well, the notes did it for me.
Right.
But yeah, you can do it in Excel. It wouldn't take you that long. You know all of the data over here.
Yeah.
Every single thing that's in that equation, I put up on the board. Except for T, of course. That's why you're making a plot. All right, so how many steady states do we get? 5 steady states. I know we did a little bit of this last time, but here's where it comes from. So let's call them A through E. Which ones are stable and which ones are unstable? A, C, and E. What brings about the 2 curves within the sigmoid, aside from the fact that there are 2 reactions? Sure, both of the rate constants are exponential. What's not equal? The rate constants? The rates aren't equal, but the rate.
The temperatures under which they undergo that exponential increase in rate.
Yeah, so I mean, it's not all because of this, but this helps, right? This is basically saying that the first reaction is going to experience some rapid increase in rate at a certain temperature, and that temperature is going to be different for the first reaction than for the second reaction. Now, this system's a little bit more complicated than that because it is a series reaction. So, for example, what would happen if? So let's say that this, you get a swing up at low T, and then B to C, you get a swing at high T. That would generate this curve, right? So this is the first swing, which is the formation of a bunch of B from A, and then later you get another exotherm, which is related to the formation of C from B. And of course, both of these reactions are exothermic, right? That's why they both shoot the temperature up when they start to occur a lot. What if this switched, though? What if, because of the activation barriers, this one happened at high temperatures, but this one happened at low temperatures? Would you expect to see two humps? Good, we have disagreement. All right, everybody said yes, get on this side of the room. All right. So why, if somebody said one hump, why?
Because it happens at low temperature. So at the high temperature, you'll start to see A go to B, but it's already too high for it to go from B to C.
So the idea is the differential change in how much C increases at that high temperature isn't much. And at low T, A to B doesn't really happen. So essentially the second reaction doesn't occur at all. But at the high temperatures.
So who said two humps? Why?
Because if you have some sort of rate loss from B to C and the K is smaller, you have way more B now, then you're still going to have it convert over. Those are examples.
So, but the question is, the question that you have to think about, and I'm not sure that I'll give you guys an answer